All right, so this is the second part of Lecture 20. The first part we covered Summary 3, and I think we made a lot of good progress there showing how to format the paper, grab the charts from Microsoft Excel, and stick them into Microsoft Word. So, good shape. Oh, and by the way, you don't have to use Microsoft products. You know, there's Google's out there. I don't know if like Lotus is still around. Or not. It used to be a spreadsheet, and then there was another software package called WordPerfect for a long time. But you know, write the thing in.
I knew Lotus better than Excel.
Lotus.
I've had some Lotus in a couple of years.
Yeah. It's. I mean, they're just tools, and then there's another pretty cool language for documenting called LaTeX. LaTeX. You know, it looks like latex, but LaTeX is a good one too. If you want to get into that, it's pretty fun. It's a lot of technical. A lot of textbooks are written in LaTeX for being able to format equations. Okay, but let's take a look at Chapter 10. We got through. Last time we got through how many nuclear reactors there are. We also looked a little bit at Einstein's equation, E equals mc squared, talked a little bit about how much energy was released or converted from matter into energy with the Hiroshima bombs. And now we're going to get into some of the physics of nuclear reactions themselves. And that's 10.3 in the textbook. And as usual, I will focus mainly on the figures. There we go. So that was overall usage. That's the number of plants. Okay, so you know you hear the term radiation or radioactivity, and you know it's not exactly a misnomer, but it's also doesn't really fully capture everything that's going on in radioactive decay. Is what we can see here. There are four main types of radiation. And the of the four types, only one of them is actually radiation. The other three are particles. So in the case of the alpha particle, that's the one listed up top. I'm just going to read that guy straight out of the book. So alpha particles. The least penetrating, so it's actually just a helium nucleus. So again, this type of radiation has mass, in fact. So what we're looking at, helium, it's a pair of protons and a pair of neutrons. Since it is as big as it is, it's going to bump into something inside a piece of paper, and the piece of paper is going to stop it. Right? It's just, you'll think of it's like a coffee ground trying to make its way through a coffee filter. It's just simply not going to make it. In this particular case that we can see here, radon is being converted into polonium, and let's go out to our periodic table and just verify that. If I'm not mistaken, I think radon is, radon is actually a noble gas, so relatively stable. You know, if you remember, you know, your normal noble gases, helium, neon, argon, krypton, xenon, these are relatively long-lived gases. The same thing is true of radon. But there's two different types of stability. One is chemical stability, And these guys are all incredibly chemically stable because their outer electron orbits are full. Once you get sort of lower, heavier, they become less radioactively stable. And the reason for that, all these little protons inside the nucleus are pushing apart from each other, so you get that many positive ions this close together, and they want to squirt off. They're going to get to a lower energy level, and in general, everything in nature is sort of always heading towards some lower energy level. Polonium is more stable, and I think the same is going to be true until you get down basically to lead. Okay. So the next type of emission, this is called a beta particle, another type of radioactivity, and that's just a really fast-moving electron. That's all that is. That electron is moving fast enough, it is going to go straight through paper, in general, on average, not statistically, but the electron itself is going to get caught up in all of the electrons orbiting the nuclei in aluminum, for example. Doesn't mean aluminum is the only thing that will stop, but it just means that some metal is going to suck in that electron. Okay, next one is a gamma ray. This is actual radiation. It's a photon. It does not have mass, and it will go. And it's not like light. If this was a light photon, it would more than likely bounce off the paper. We'd see that as the white light reflected, and it would almost certainly bounce off the aluminum like you would in a mirror. But it's moving fast enough with a short enough wavelength that's going to pass right through the paper, right through the aluminum, and not unless you have a certain critical thickness of lead is that gamma particle going to be stopped. The next one is a fast-moving neutron, and so just imagine this. So here's a shot of a beta particle being ejected. And what I failed to mention on the beta particle is that the electron actually comes out of the nucleus of the atom. It's not just coming out of an electron orbital. So and when that electron comes out, what you can see is that the mass of the nucleus doesn't change. We started out with iodine 131. So here's iodine 131. So relatively heavy. Your average iodine nucleus or atom has a mass of 126.9. This guy is more massive. It's because it's got a lot of extra neutrons in there. More neutrons than the average iodine nucleus. When that electron fires out of there from iodine, it leaves behind a proton. It's kind of weird. There was a neutron sitting inside that iodine nucleus, and it turns into a proton and an electron. The electron says, "See you later." The proton stays behind, and now what used to be iodine is now xenon. So very fundamentally different from our normal experiences with chemistry. This is happening at the nuclear level. Okay, so there's your beta particle being ejected. There's no picture of a neutron being ejected, but you could imagine. Let's just say, for the sake of argument, this is also iodine 131.53. If this were a neutron coming out instead of an electron, what you'd be left with would be iodine 130.53. It would just be one atomic mass unit lighter. All right. And there's a little box there, box 10.2. Basically tells you, and I'm not gonna work through it. What it's showing us here, though, is that the neutron has a mass that's slightly larger than the proton, so 1.00867, units versus 1.00728 units. The electron itself is 0.00055 units. And what the math that follows shows is that the three numbers don't actually add up. So when the neutron turns into a proton and an electron, there's some leftover mass that has not been accounted for, and that more or less tells you what the energy is. And it says all of this energy, this 0.78 mega electron volts, all of it becomes kinetic. And by kinetic, it means just the sucker's moving really fast. The electron's smoking out of there. It would be ejected as a penetrating beta particle traveling about 3/4 the speed of light. So it's honking too. It's got a lot of energy. All right. Now this is important. This is important. We will do a little bit of math on this guy, because you're going to have a question on the exam, and this is a question that I'm not sure why, but seems to frequently baffle people as to how to answer it. But I'll show you exactly how I want this question answered. Here's the basic principle behind radioactive decay. So we're going to just start with a certain amount of material. This is just going to be, time equals 0. And then at some later time, and I'll just use the example from the book. I'll just, let's see, 6, 12, no, 8. I'll just say 8. Yeah, let's go with 8. Time equals 8. Go a little bit later. Time equals 16. A little later. Time equals 32. This is an example of radioactive decay, and the time in between each interval is, I'm just going to call it T1/2 equals 8. And so what it means, if I wait 8 days, only half of my original sample is going to remain. Wait another, only half again. Another, only half again, sort of ad infinitum. So 8 days, 8 days, 8 days, on down the line. This stuff can become a little bit confusing because there are different ways to do it, but let me go out and look at half-life. You can see that one way to do it is just say I'm going to start with a certain amount. So this N naught, this N0 is just this much. Right here, this is N naught. This is going to be N1. This is going to be N2, etc. N3. So that's what's meant by this. So N as a function of time. And there are a few different ways to do it. And I think getting back to that summary 3 exercise, you can either divide by the time constant or multiply by the decay constant. Is that kind of making sense now? And they're just a reciprocal of each other. There's this other thing called the half-life. But in that case, you're not using an exponential, you're using you're using 1/2 to this power, t divided by the half-life. Now, here's the half-life right here. Here is the decay constant, and here is, they're calling it the mean lifetime. There we go. So half-life, decay constant, and the mean lifetime, or how long this thing this thing lives. So what I'm going to ask you to do is, if you, and again, there are multiple ways to do it, but all I want to see in the exam is if I give you, we can just say n naught, let's just make up some number, equals 100. N1 is going to equal 100. And let's just use the top one. Let's just use the half-life. So 1/2 and we're going to take this to the power t divided by the half-life. T divided by t half-life equals, now so for n1, we know for n1 that time actually equals 8, so n1 equals 100. Now don't be tempted to multiply the 1/2 by the 100. The 1/2, you have to operate on the 1/2 of the exponent. You know, so my dear Aunt Sally, but there's another one. Whatever was it? P parentheses exponential. PE, my dear Aunt Sally, or whatever it is. Please excuse my dear Aunt Sally. So we'll do the excuse part here. Thanks. Okay, so we're looking at 8, and the half-life is in fact 8. We already wrote that. Equals 100 times 1/2 to the first power equals 100 times 1/2, because anything to the first power is 1/2 equals 50. So the math works out. And that's all I want to see you do in that problem. Is just give me an example, let me know you know what a half-life is, and type out a kind of a simple little equation like this. You don't have to be super fancy with it, just something that you can put the language of what a half-life is with the numbers, and then just demonstrate proficiency with manipulating it, just like I did. If you want to use the exponential, that's fine. I don't have a preference. There's multiple ways to the right answer, but I just want to see something like this when you answer that question. Okay.
So what if you did N2, would that be 16 over your half-life?
Yeah, let's try it out. N2, we'll do it really quickly. N2 equals 100, and then we're going to do 1/2. T equals 16, yep. And then you still have 8 in the denominator, equals 100 times 1/2 to the second power equals 100 times 1/4 equals 25. Pretty simple. Yep. It's pretty easy to work with that 1/2 rather than you can kind of do it in your head versus working with the exponential. But if you want to use the exponential, go into a calculator or Microsoft Excel, and it'll do the math for you. Those computers are better at math than humans are, at least this kind, arithmetic. All right. Okay, so there's exponential decay, a half-life example. All right, so here's some of the leaders, the pioneers in radioactivity. Enrico Fermi, and I think it's mentioned here somewhere in the book, he actually demonstrated one of the first sustainable critical mass experiments. This had to be done prior to developing atomic weapons, and he did it under the stadium in Chicago. If you're ever through Chicago, you can actually walk. They've preserved the lab. You can actually walk in there and see the original experimental setup. It's quite something. Otto Hahn, again, sort of born at the right time to be studying this kind of thing. Started out with chemistry in Germany, worked with Rutherford. Rutherford is, he's mentioned here as well. More or less is a attributed to having discovered the structure of the atom, that matter at the atomic scale is pretty sparse. There's just not a whole lot there. You've heard if you've got a football stadium, the nucleus is about the size of a pea sitting down the 50-yard line, and everything else is empty space, and the electrons are flying around the ball. He did some very careful, delicate experiments where he was shooting particles through thinner and thinner films of gold, and sometimes it would just pass right through. And he's like, well, based on the fact that the stuff is just going right through solid matter, means solid matter is not so solid. And down here at the bottom, figure 10, Lise Meitner studied physics in Vienna, moved to Berlin, 1907. Barred as a woman from the Maine department, and you hear about this all the time. It's really too bad we used to behave that way, and to some extent still do. She was allowed as a special concession to Otto Hahn to use a spare room on the ground floor. By 1930, she was head of physics. Being an Austrian citizen, she was allowed to continue despite her Jewish background. And again, this is all during the war. She left, traveled with Bohr, but didn't join the Manhattan Project. If you don't know what that is, it's the actual Los Alamos and Oak Ridge, Tennessee, various other labs around the country to build a nuclear weapon. Sounds like she was objected to partaking in such activities and stayed in Sweden where they awarded the Nobel Prize. I don't know if she got one or not, but it's not a bad place to be. Okay, so what we're mainly looking at the moment is fission. We talked a little bit already about neutrons being ejected from nuclei. In this case, what we're looking at is a uranium-235 nucleus. Now, what's special about 235 versus 238? There are fewer neutrons, obviously. 238's got more neutrons. What are those neutrons doing? They're making that nucleus more stable. They're more or less shielding the protons from each other, allowing it to be more stable. The 235 is the perfect fuel because it's unstable, but just unstable enough. Kind of like gasoline. I mean, gasoline is, unless you get a match to it, it's going to slosh around your tank. It's not going to blow up. So same thing. U-235, just unstable enough to act as a nuclear fuel. So here comes the neutron. The thing gets a little bigger. Now, for reasons that I don't completely understand, the 236 is even less stable than 235 or 238. It's just kind of a, and again, if I were a nuclear physicist, I would say, well, it's because this one little neutron is bouncing around, and lets those two protons get closer together, and once those get closer together, they sort of form this budding formation and go unstable. So there's way more going on down here in the nucleus than your average mechanical engineer understands. But nevertheless, 236 itself is unstable, which forces the two nuclei apart, and when that happens, a big mess of other particles come off. So the betas we talked about, the gammas, the neutrons. So you could imagine in the next step, this neutron is going to smack into another U-235, and this is what all the Manhattan Project folks were, busy scribbling down. How much do you need before the thing actually blows up? How close together can they be before it becomes unsafe to transport, et cetera? So, kind of a messy business, literally, but there it is. Okay, box 10.4. Let's see, we got 13 minutes left. I'm going to take a quick break and then kind of hustle through the rest of the chapter. This actually is pretty good reading. I'm just going to take a quick break and I'll hit the highlights because I think we got to wrap this chapter up. But I love talking about this stuff and I love thinking about it.